Let's take some attendance with your clickers. Okay, now you can click. Could I get some help handing out some handouts? Who are my helpers here? Oh, thank you so much. Oh, got another helper over here.
Okay.
Thank you. Over on this side, helpers. Okay, that's right there. Thank you. Okay. Wait. Through there,
We say it at 99.
Yeah, because I have this. Figure it out. That's
Thank
fun
you.
too.
Okay, last day, we talked about equilibrium. And equilibrium was just balance. It's just a situation where there was no acceleration. And that means there's no net force and all the forces have to balance out. And how we recognize that is with the wording, constant velocity. If you see those words associated with the problem, ding, 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 that's an equilibrium problem. And you want to balance your free body diagram. Now, in this particular problem that we've just handed out, we have this block that's going down an inclined plane at a constant velocity of 2 meters per second. And here's the thing. We don't care about the 2 meters per second. It could be 102 meters per second. What's important is that it's constant because that's zero acceleration. Now, in this case, we're told that the normal force exerted by the ramp on the block is 80 newtons. And we're asked to find the mass of the block. Well, that's kind of backwards from what we're used to. Usually we're given the mass and we're asked to find the normal force. But I give you this old exam problem to show you that you could be asked to dance backwards. Okay. We're also asked to find the coefficient of kinetic friction. Again, that seems backwards. Usually we're given that coefficient and we use it to find the friction. Well, let's see how we can do this. Let's work this together. How do we start a dynamics problem? What's the first step? Free body diagram, of course, of course. Okay, so the first force we put on any free body diagram is going to be the weight force, Earth on the block. And then I ask, are there any magnets? No, but we'll get plenty of those on Thursday. So what touches the block? The ramp. Does it push or does it pull? Not a rope, not a chain, not a thread, not a one of those things. Anyway, it pushes, and whenever one thing pushes on another, there will always be a normal force by the ramp on the block, and that's going to be 80 newtons. That's given in the problem. I know that if I didn't have friction, it would speed up as it came down that ramp, so there must be a friction force. Let's draw it straight. And that's gonna be kinetic friction, because I can hear the scraping. Well, you can hear it, I can't. But it's there, okay? And we don't know how big that is. But that's our free body diagram. We followed the recipe, we're done. Now, whenever you have a ramp problem, you want to rotate your coordinate system so that it lines up with your ramp or hill. And if you do that, all of the forces are good. This is going to be lined up with Y, that's going to be lined up with X. It's always the weight that needs to be broken up into its components. And we do that what I call the right way. We look in the direction of the normal force, we go the other way. Now, do I go all the way down here and then come over level? No, or heck no. Sick and wrong, sick and wrong. No, 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 no. Don't do that. You want to come down until you can take a 90-degree turn and get to the end of the weight. This has to be 90 degrees. And if you break it up that way, you're guaranteed that this angle of the hill is going to be this angle between the Y part of the weight and the total weight. That's this one here. This would be the X part of the weight. Now, once you have broken that up into its parts, you use the parts, okay? Use the parts. Now, the fact that this is acceleration 0, equilibrium, means that this diagram has to scream balance in both directions. And that means in the Y direction, well, F net in the Y direction is equal to MAY, and that's 0. So that means the net force is 0. And that means this 80 newtons in the positive Y direction has to be balanced by this Y part of the weight. So this must also be 80 newtons, okay? Does everyone see that? I've got one force in the positive Y direction, one in the negative Y direction. So that means that the normal force by the ramp on the block is equal to the Y part of the weight. And since the normal force is equal to 80 newtons, so is this. Okay. Well, how does that help me find the mass of the block? Well, let's think about how we would have proceeded if I gave you the mass of the block. If I told you, I just make this up. If I told you the mass of the block was 10 kilograms, how would you find this total weight? Quick, quick, quick.
10.
Yeah, multiply by 10, it'd be 100, okay? And then if you knew that this was 100, how would you find WY, the Y component? Yeah, you take 100 times the cosine of 37 degrees. Well, let's do that. Let's say the Y part is just the total weight times the cosine of 37 degrees. Well, we know that this is 80 newtons. I'm looking for this. And I know that the cosine of 37 degrees, that's one of the ones I know, it's 0.8. Okay? So now I just divide both sides by 0.8. And the gravitational force is going to be 80 newtons divided by 0.8, and that gives me 100 newtons. Well, the mass of the block is just going to be the weight of the block divided by G. Well, that's going to be 100 newtons divided by 10 kilograms. I'm sorry, that's not right. Newtons for each kilogram. And that gives me 10 kilograms. See if your neighbor followed that. See if your neighbor saw what was happening there. Okay.
Oh, yeah, probably.
Oh, yeah, take one.
Once,
It's not coloring.
once I know that the total weight is 100 newtons, I can find the X part of the weight. Well, this is a 3, 4, 5 triangle. This is going to be 3 times 20, 4 times 20, 5 times 20. So this is going to be 60 newtons. Okay. I can do Newton's second law in the X direction. Again, the acceleration is 0 in both directions, it's balanced in both dimensions. And so this is going to be 0. And that means that the friction force by the ramp on the block is just going to be the X part of the weight, which is 60 newtons. Well, now I can use that formula for kinetic friction. And whatever indices I've got here, ramp on the block, I need the same indices here. In a lot of problems, we have more than one normal force. And so figuring out which normal force to use in my friction equation is just the indices. Again, they save us. So if the friction was 60 newtons and the normal force was 80 newtons, I can now find a coefficient of kinetic friction as 60 newtons divided by 80 newtons, and that's going to be 0.75. Check again on your neighbor. This is an old exam question. These are the types of questions you can expect on your exam. Oh, if you let this hill go flat and you have a spike, this will be horizontal and this will be vertical. But if I move this board up 37 degrees from horizontal, this spike is forced to move 37 degrees away from vertical. Well, this spike that's always perpendicular to the board, that's going to be this Y part of the weight. And straight down, that's going to be vertical. That's going to be the total weight. And so that's the spike moving away from vertical as the board moves up from horizontal. Okay. Other questions on this problem? Okay, let's talk about something different.
Oh.
On the back of that sheet, there's a problem that I call the gauntlet. And that's because I put this on an exam the first year I was teaching at Montana State University, 33 years ago, 34 years ago. Anyway, I found that in my large lecture class of 350 students, nearly everyone got parts A and B right. And then people started having trouble. And as we went down that problem, part after part, more people started making mistakes until only a handful of my students, again in this large lecture class, got the last part right. So we don't have time to do that problem today. We will go through it on Thursday. But before then, I would encourage you to give it a try. See how ready you are for this exam. See how far you can get through the gauntlet before you get tripped up. Okay? It's going to be fun. Let's talk about uniform circular motion. Your gut knows what I'm talking about. I'm talking about this, okay? And so the question is,
Give my phone.
what's uniform? what's uniform about what I'm doing here? Raise your hand, brave soul. Yes, sir.
The velocity,
Constant velocity. Well, my velocity vector doesn't look like it's staying the same. What other ideas do you have?
Constant acceleration.
Constant acceleration. Well, remember what we learned in that second tutorial. If I've got cruise control on, the acceleration is always perpendicular to my velocity. That acceleration vector doesn't seem to be staying the same. Oh, yes.
the speed,
Speed, yes, speed. You essentially put cruise control on and your speed stays the same as you go around this circle. Now, the direction of the velocity is always tangent to the circle. The direction of the acceleration is always perpendicular to that velocity, which for a circle points towards the center of the circle. That's old news. That's where we've been before. That's the second tutorial. What we haven't done yet is found the magnitude of that acceleration. And that's what I want to do really, really quick with the help of this guy, Galileo. He was the first one to figure this out. And his derivation is so beautiful that it makes me weep sometimes. And I think maybe it might make you weep too. Let's look at what Galileo said. He said, suppose something's going in this circle at some constant speed, not velocity, but constant speed. And at noon, that object is right up there. And a little bit after noon, it's moved over there. Now, Galileo understood that acceleration is how much the velocity vector changes in a unit of time. And so he took those vectors, the one at noon and the one a little bit after noon, and put them heel to heel, tail to tail. That's how we find a difference between vectors, okay? And then he argued that this angle here had to be equal to that angle there, okay? How do you see that? Well, it's almost Halloween. Imagine you're being chased by the Grim Reaper, and he's got one of those scythes or whatever you call it, you know, with the blade, okay? And if he's holding it vertical, then the blade's like that. And if he's swinging it down at you, whatever angle he brings the handle down away from vertical, that's going to bring the blade down from horizontal. So that angle has to be equal to that. That just too morose? Okay. Happy Halloween. I don't like that holiday at all. That's not my favorite. Okay. Galileo knew that he was looking for this vector right here. The change in velocity, what I have to add, there's the plus sign, to my initial velocity, that's that. I add this change to turn it into that final velocity. Now, this is where he used his genius. He said, look at that arc length right there. Well, that's just how far you traveled in a little bit of time after noon from here to here. And that distance is how fast you're going times how much time elapsed. You know, if you're going 50 miles an hour for 2 hours, you've gone 100 miles. It's that simple, okay? And then Galileo said, this triangle is similar to that triangle. And all of his contemporaries said, oh, Galileo, you silly boy. That's not a triangle. That's a slice of pie. That's a curve. But Galileo said, yeah. But if I look at a smaller little time interval, this becomes a narrower piece of pie. And this arc here starts to look more straight. And I can just keep on making that delta t smaller and smaller and making that slice of pie narrower and narrower until it's really straight. What Galileo was doing was taking a limit as delta t time went to zero. He was doing calculus, and that's important because calculus hadn't been invented yet. Newton invented calculus after Galileo died, yet he was using the principles in this argument. So if these are similar triangles, then Galileo could say the green part of this triangle divided by the green part of that triangle is equal to the long side of this triangle divided by the long side of that triangle. Everyone see that? Similar triangles? Okay. And then Galileo was almost there. He knew what he was looking for was delta V over delta T. And he said, oh, I'm almost there. I've just got this pesky little velocity there. Let's get rid of it by multiplying both sides by V. And he gets this result, V squared over R. And that's the formula for what we call centripetal acceleration. Centripetal is just Greek for center seeking, towards the center. And that's the direction it points, is towards the center. See if your neighbor's weeping from that derivation. Do a buddy check.
Yeah. You can follow that.
Okay. Now, I'm going to derive it a different way with the help of PowerPoint and just being careful with the length of vectors. Suppose you're going around this circle in some sort of vehicle and you've got cruise control set at 30 miles an hour. And if we want the acceleration right at this dot, what we could do is look at the velocity a half second before and a half second after that dot, okay? Because that's what acceleration is. How much the velocity vector changes during 1 unit of time, 1 second. So if that's noon, this is what your velocity looks like a half second before noon, and that's a half second after noon. Now they're the same length because you got cruise control on, but they're not the same direction. So I look for how different they are by putting them tail to tail. I pick this one up and move it down so that they're tail to tail. And then the change vector is what I have to add. There's the plus sign. This was a half second before noon, then plus this change gives me a half second after noon. Okay? Now, because that change happened in 1 second, that is the acceleration. That's how we define acceleration. And we've got a C there for centripetal. That's the steering wheel acceleration. Okay? Now, what if I went around not at 30 miles an hour, but 60 miles an hour? What has to change in this picture? And there's 2 changes. Talk to your neighbor. What has to change in this picture?
Right.
Okay, brave soul. What? Cowards. There you go.
Size of the acceleration vector.
Okay, we're going to find that the acceleration vector gets bigger. But what about the velocity vectors? Oh, I'm sorry. I wasn't on the right slide. Okay, that's 30 miles an hour. My bad, my bad. What happens to the length of those velocity vectors? Get twice as long. If I'm going 60 miles an hour, they would be twice as long. What else changes? There's another change that happens there.
Where they are on the track,
What that?
where they are on the track.
Yeah, where they are on the track. If you're going twice as fast, a half second, you're going to cover more ground. And so instead of being here and here, they would be further away from the dot, twice as far away. Thank you very much. Now, those 2 vectors are very, very different from each other. And when I look at that difference, there's the plus sign right there. This is the change. And that change, because it happened in 1 second, is the centripetal acceleration. If I compare that to what we got before, carefully using PowerPoint, I find that it's 4 times bigger, twice as fast, 4 times the acceleration. That tells me that that acceleration must depend not on speed, but on speed squared. Speed squared. Well, now let's go back to the 30 miles an hour. And instead of going around this gentle track, let's go around a track that has half the radius. You see that my velocity vectors are the same length, but because this is a sharper turn, the direction of those dark red arrows are more radically different from each other. And so if I look at how different they are, this is for the small radius, this is for the large radius, and if I go and compare them, I find that the small radius has twice as much acceleration. So if I cut the radius in half, I double my acceleration. That suggests that this acceleration depends not on radius, but 1 over radius. And so once again, I get the same answer that Galileo got without PowerPoint. Okay, so this is the summary. Centripetal acceleration is just a special name we give the steering wheel acceleration when we're going at constant speed around a circle. Okay, and it's perpendicular to the velocity, which for a circle points towards the center of the circle. Hence the name center seeking. And this is the new stuff. And this will be on the front page of your exam, v squared over r. The acceleration is v squared over r. Check on your neighbor real quick. Check on your neighbor. Okay. How many of you have been on something like the rotor before? They don't call it that anymore, but this is what they had when I was alive. It's a room, a circular room. You go in, they spin you up, and then they drop out the floor, and you're stuck to the wall. Let's watch a quick video of that. There we go.
As the rotor house begins to spin, what forces are acting on the people inside? Draw a vector diagram of the forces that are on the people as the rate of spin increases. Notice how the beach ball moves. What is the direction of the resultant force on the ball? When the final spin speed is reached, the floor of the room is removed. Describe what is happening. Describe the motions that you see these people making. How would they explain the forces that they feel? How is their description likely to differ from yours, an impartial external observer?
Good enough. Okay. So we were told that we should talk about this ball that we saw move towards the outside, and we want to know what direction the net force is on that ball. And we were asked to draw a free body diagram for that ball. I'll start us out. The weight force always points straight down. What next? No magnets. What touches the ball? String. And the string can only pull in the direction of the string. So that'd be that way. But I saw that ball move to the outside. So what other force would I have there? What other force? Brave soul. What would that force be called? Yes.
Friction?
Friction? Friction's usually nooks and crannies that are scraping against each other. There's no nooks and crannies here. Is it a normal force? What labels would you put on that normal force? All forces are exerted by something you can taste, smell, touch.
Centrifugal?
The what?
Centrifugal?
That's a name, centrifugal, but that's not a thing. That's not something I can taste, smell, touch. That's a concept, an idea. Folks,
The air?
is it air? I forgot to mention, if you suck out all the air in that room, the beach ball still goes out. The ride's not as fun, but the beach ball still goes out. Folks, I want you to put this in your toolbox. If you cannot find a boogeyman to blame that force on, it doesn't exist, okay? If you can't label the force, it probably shouldn't be on your free body diagram. There's nothing touching that ball except for the string. And we already took account of the string. And so that force, that outward force, doesn't exist. Doesn't exist. Okay? That's my free body diagram. And that free body diagram doesn't scream out, it screams in. You remember that whenever we had a force off at a goofy angle, we broke that force up into its components, its Y part and its X part. And then we threw away the original and used the components. So that free body diagram looks like that. And it's pointing towards the inside, towards the center of the room. Does that make any sense? Well, yeah, because we know that something going in a circle has acceleration towards the center of the circle. And the acceleration is caused by the net force. So that means if I've got acceleration towards the center, my net force has to be towards the center. But wait a minute, Greg. I specifically saw that ball move out. I saw it with my own eye move out, not in, out. But I was watching it from the lens of a camera that was in the rotating room. I was watching that ball from the point of view of an accelerated reference frame. Now, what if we were to look at things from the point of view of Jonathan Livingston Seagull, who happens to be hovering over this ride? And because of his magical powers, he can see right through the roof. What he sees is Billy and the ball going around in a circle. Well, things don't naturally want to go in circles. Things naturally want to go straight. That's Newton's first law, Galileo's law. Okay? Things in motion stay in motion in a straight line. If Jonathan Livingston Seagull could use his magical power and suddenly disappear the walls of that rotor room, what happens to Billy and the ball? They go shooting off in a straight line right over that popcorn vendor. That's the way they want to move, okay? Now, what's keeping them from going in a straight line? Well, for Billy, he's trying to go in a straight line and the wall just keeps on pushing him back into a circle. Now, it feels like to him like he's being pushed into the wall, but actually it's the wall pushing on him to make him go in a circle. For the beach ball, it's trying to go in a straight line, but the only thing keeping it in the circle is the only thing touching it, which is the string, okay? If he let go of the string, the beach ball would just be up against the wall and it would be the wall that's pushing it in the circle. But the force is in, not out. Let me give you another example. Suppose you're on a big, big pond of ice. You're ice skating with your friend, and she's way over there. And suddenly she calls to you and says, I'm coming really fast. Make me go in a circle. Okay? And she comes racing towards you. Well, you dig in with your skates. You're trying to anchor yourself. And when she gets right next to you, do you push her? No, that would be mean. Okay? No, you grab onto her and you pull to make her go in a circle. Now she's going to feel like she's, being pulled out by something magical. But in truth, you're not magical. You're just pulling in, and it feels like she's being pulled out. See if your neighbor followed that line of thinking.
Third law, right?
Well, there are third law pairs for all forces. So my pull on her would be equal to her pull on me.
Yes, she is pulling, but she's not being pulled out.
No, she's being pulled in, and I'm the one that's being pulled out.
I think so.
Okay. Now, for an object moving in a circle, the acceleration points towards the center of the circle, and therefore the net force has to point towards the center of the circle. And here's where I owe you an apology on behalf of all the physicists that went before me. We did something very, very unwise, very foolish. We gave this net force a name. We called it the centripetal force. And that's a mistake, because when you name something, it becomes real. If you grew up on a farm or a ranch, you know that if you name that pig, you're not eating it for breakfast. Okay, that's family. Okay, once you name it. Okay, and that's what happened with this net force. By calling it centripetal, a lot of beginning students think it's a new flavor, like friction and normal and tension. Oh, and centripetal. Not so. A net force is just a mathematical idea. It's not a new real force. It's just take all the real forces and add them up. Same with this centripetal force. It's just all the real forces added up. So if we go back to our example here, there's not a new centripetal force on my diagram. I just add up all those forces, and the upward Ty cancels the downward weight, and the net or extra force is just the X part of the tension. That is the net force. We call it centripetal, unfortunately. Now, what about that centrifugal force that Madonna used to sing about long before you were listening to music? Okay. It just isn't there. Okay. It's not there. There is no such force, regardless of what Mr. Wizard says. Now, this is a painful memory for me, but back in grad school, MIT had a special television channel where they showed all sorts of educational programming. They had professors working homework problems on this channel, and they also had Mr. Wizard. And that's what I would do with my children whenever it was my turn to watch the kids when my wife was at the hospital working. Okay, we would sit on the couch and we would watch Mr. Wizard. That's how geek families bond. Okay, and one day I remember Mr. Wizard was at a what do you call lagoon? An amusement park, yeah. And they were on the roller coaster doing a loop-de-loop, and suddenly he started talking about the centrifugal forces on those people. And I just jumped up off of the couch and I punched off the TV and I said, you may never, kids, you may never, ever, ever again watch Mr. Wizard. Okay. And that's one of the rules that we have in our house. We've raised 4 wonderful, wonderful children, and we only had 3 rules in our house, and that was one of them. You may not watch Mr. Wizard. So That's just what we chose to do. Okay? I'm sorry, what? You want to know what the other two are? No sex on the first date. And you can't date the same person twice. And that worked for us. That's, you know, you choose whatever rules you want to enforce in your house, but I'm just telling you, it worked fine. Thank you. So now let's practice this with a demonstration here. I've got a bucket and I'm going to put about 1 kilogram of water in there. Okay. And then I'm going to rotate this in a vertical circle. And what we want to find is the normal force by the bottom of the bucket on the water when it's up at the top, and then again when it's down at the bottom. Okay? And so, oh, darn. Child play. Okay. Now, we start with a free body diagram. The first force we put on any diagram is the gravitational force, Earth on the water. And then I ask, any magnets? No. So what touches the water? Well, the bucket, okay? And that bucket is pushing. It's not a string, not a rope, not a chain, not a thread. And so it's pushing. And the sides are pushing in all directions. And that's going to cancel out. It's only the push by the bottom on the water that's going to not cancel out. And because the bottom of the bucket is above the water up there, I'm going to have a normal force that is down, okay, by the bottom of the bucket on the water. Everyone see that that has to be a force down because the bottom of the bucket is above the water, okay, and it's a push. Now, what direction is the acceleration when the water is up there? Yeah, towards the center of the circle, straight down. And so this diagram screams the direction of the acceleration. That's good. That's good. Okay. Now, I have a question. Why doesn't the water fall on Greg's head? Some of you are saying, yeah, that's what we wanted to see. Yeah. Why? What reason can you give for that? See if your neighbor knows. See if they're just being shy.
Like.
Okay. So, what is it? Why doesn't it just come falling down on my head? Well, if I just held the bucket over my head, surely it falls straight down. But the bucket isn't stationary up there. It's moving with an acceleration that's perpendicular to that velocity. And again, we know from the second tutorial that anytime my acceleration is 90 degrees to my velocity, I'm turning, okay? That's turning. And so it's not going to take that water straight down. It's going to take that water around the circle, okay? Now, we want to know how big that acceleration is in order to do our calculation. So we have to make some approximations, okay? We know the formula is v squared over r for centripetal acceleration, but what's r? Okay, well, we're dealing with Greg. So what's that radius there? Let's call it 1 meter. And there's a picture of Greg that shows that it's about 1 meter, okay? So what's my speed? What's my v? Well, let's say that I make this go around once every 1 second. So 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000. Okay? So if I take delta t to be 1 second, and I take the radius of my circle to be 1 meter, then it goes a distance 2 pi r, 2 pi times 1 is 6.28 meters for every 1 second. So it's about 6 meters per second. That seem fair? About 6 meters per second. So if I plug into this formula up here, I get 6 squared divided by 1. That's going to be 36 meters per second squared. 6 squared divided by 1. That's just an approximation, okay? Now, we have to answer a really fundamental question, and that is my total acceleration this centripetal acceleration of 36 meters per second squared, or do I have to add gravity, 9.8, call it 10, to get 46? Okay, so with your clicker, tell me which of those you think is the right acceleration. I'll get you started here. Okay, now you can click. Okay, get your vote in. Last call.
No.
Oh, we're pretty evenly split on that. Pretty evenly split. Okay, let's talk about that. The answer is 36. 36. We don't have to add 9.8. We don't have to add gravity. And let's see why that is. Acceleration is nothing more or less than how much the velocity vector changes in 1 second. And when we were doing our little calculation here, we didn't care whether this circular track was a horizontal track or whether it was a vertical track. We didn't care whether it was a car going around a track horizontally or whether it was a daredevil on a motorcycle going around a vertical track. All we cared about was that this vector changed into that vector, okay? And we got the formula v squared over r. And because that change happened in 1 second, that was the centripetal acceleration, okay? Oh no, why do you do this to me? Okay. Now, which of these forces causes that acceleration? Both. Yeah, some of it's caused by gravity, some of it's caused by the bucket pushing down. Okay, both. Okay, both. Okay, so we can figure out how big that normal force is. Remember, that's what we're trying to do. With the acceleration of 36 meters per second squared, and if I have, what did we say that was? That was about 1 kilogram of water. Yeah, so that's going to be a net force of mass times acceleration, or 36 newtons. This diagram has to screen down by 36 newtons. And a weight of 1 kilogram is just 10 newtons. So what's wrong with my free body diagram? What's the mistake there?
So your normal force is
How big does that normal force have to be? Has to be 26, okay? It should be 2.5 times as long as that weight force. It just isn't drawn to scale, Okay, does that make sense? Check on your neighbor again, really quick. Could be.
bigger time.
Okay, questions? Okay, what if I were to swing it a little bit slower? What happens to my acceleration? Well, it's v squared over r, that's going to get smaller. What happens to my free body diagram? Okay, does the weight of the water change? No. That means that this normal force by the bottom of the bucket has to get smaller. And if I make that smaller and smaller by going slower and slower, eventually that normal force between the bottom of the bucket and the water is going to go to zero. And then what happens, folks? Yeah. Okay. Let's do that demo. Okay. So I go 1,000, 1,000, slower, 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 slower. I've got sponges in there. Bazinga. So this morning I put too much water in there and I got drenched. So that didn't always work. Back in Montana, we didn't use sponges. We had a special powder that we would put in the bucket. And when we poured water on the bucket, on the water, when you poured water on the powder, it became a very, very stiff jello jiggler sort of stuff. It just went solid. And our demo guy retired and we hired a new one. And he asked me, he said, well, Greg, how much powder do I put in this bucket? I said, I don't know, Jerry. Mark always did it. Just put some in. Well, Jerry was always pretty thrifty and he didn't want to waste any, so he didn't put enough in. And when I lifted it up over my head, it was just yellowy, like just slime all over me. It was just nasty, nasty. So now we want to do the bucket at the bottom of the swing. Let's move that bucket down here and see how things change. At the bottom, what direction is the acceleration? Yeah, it's got to be up towards the center. So let's draw a free body diagram. We put the weight on there. Now the bottom of the bucket is below the water, so it pushes up. But my acceleration has to be towards the center of the circle. So what does that tell me about the normal force compared to the weight? Got to be bigger. It's got to be bigger. Got to be a lot bigger. Okay. Now let's find out how big it is by using Newton's second law. This is still 36 meters per second. V squared over r didn't change in magnitude. The vector just changed direction. Okay. But now if I use the 1 kilogram to find the net force of 36 newtons, the net force has to be up. My diagram has to scream up by 36 newtons, and I still have 10 newtons down. So how big does that normal force have to be at the bottom of the swing? Tell your neighbor real quick. Yeah, it's got to be 46. It's got to be 46 newtons. So it's bigger at the bottom than it is at the top. And you have experienced this when you went on the Ferris wheel. Okay, if that Ferris wheel is going around at a constant speed, at the top you feel light. You feel like there's not much pressure between your bottom and the seat. Okay, but when you get to the bottom, you feel like you're being pressed into the seat. And that's because at the bottom you were going towards the ground, and then it scoops you up and takes you back up into the sky. And that scooping is what, makes you feel like you're pushed into the seat. Okay. Everyone feel like they could do some circular motion homework problems and exam problems? Any questions? Okay, I need my helpers again. I've got a pretest here. Thank you. Helpers over here. Thank you. This pretest has two sides to it, front and back, as soon as you get it, pretend it's, an exam and start writing. See. You have any left over? Okay. Who doesn't have one? The people back here. Where are their extras? There should be plenty. That's all we got, huh? Raise your hand again if you need one. Okay, thank you. Boy, that was cutting it close. Loaves and fishes. Any more needed? By show of hands, how many of you have finished the front page of that pretest? Okay. Most of us. Okay, let's share our answers with our clickers. The acceleration of book A is less than, equal to, or greater than the acceleration of book B. Let me get you started. Okay, you can click now.
Brennan wants the. Swing two or the last.
Okay, last call.
To some degree.
Okay, most of us said equal to. And that makes sense because they're moving together. If we tie your back bumper to my front bumper, and if you go from 0 to 60 miles an hour in 5 seconds, so did I, or else one of us lost a bumper, okay? And that has nothing to do with any special quality of the rope other than the fact that it doesn't stretch. It's not a bungee cord. And so when you speed up, I've got to speed up. Okay, one more clicker question here. The force exerted by string 1 on book A is less than, equal to, or greater than the force exerted by string 2 on book B. Okay, now you can click. Okay, last call. I think that's all of us. Okay, here we're pretty divided between less than or greater than. That's okay. We're going to talk about this in detail on Thursday. This is as far as the morning class got. And so why don't we call it a day? Go somewhere else.
Oh.
May the net force be with you. Oh, what's the answer? The answer is greater than. Okay, greater than.
Is greater on the. Wrong. It doesn't, that doesn't make any difference. Or the area impact. You're talking about the screen.